Good morning. We're really lucky to have Ellen Silbergeld, Elizabeth as she's called in Wikipedia. But she's really Ellen this morning as a speaker, and she comes from the Department of Environmental Health and Engineering here in the school. And that engineering part, which I didn't remember, was recently added. Anyway, but she lives on the 6th floor, so fortunately I get to see her pretty often. And I saw her at University of Maryland, where we were also, and Bobby also saw her and knew her there. Let me tell you a little bit about her, and she can tell you more, I'm sure. She went to Vassar College and was an engineering major, I think, or no, you weren't. But she horticulture. But she came to Johns Hopkins to Homewood and majored in environmental engineering at that time in the 70s, 1972 she graduated. And from Vassar she graduated summa cum laude and then came here to Johns Hopkins to Homewood, where she was in environmental engineering. The best part is that she's from New Hampshire. So I always like to meet New Hampshireites, and I forgot to tell you that part. Anyway, she's now professor, as I said, in environmental health and engineering here at the School of Public Health, and she was at University of Maryland across town at the School of Medicine. And I always took her to be in epidemiology, but I don't think you were. You were? Oh, good. But you were on a different floor from me, so that was great. That's where I got to know her. She's done a lot. She's been an editor-in-chief at Environmental Research and on many other editorial boards. And she's especially been involved in some of the toxicologic manifestations of lead and mercury poisoning, and did some of the early research on the effects on the central nervous system. Currently, she's working on animal food production, and she has a recent book called Chickenizing, Farms and Food, which probably will come into what she's talking about, I'm not sure. But anyway, it's a book published by Johns Hopkins Press, and so if you go up to Mount Washington, you'll see it in one of those windows, but you can also buy it locally or whatever. She won a MacArthur Award, a Genius Award in 1993. That was very exciting then to have her recognized for her contributions in toxicology. And then I'd say about 10 years ago, I'm not sure if I'm right, she decided to bring to her field, toxicology, some of the tenets of evidence-based healthcare, such as the work of the Cochrane Collaboration. And she's worked a lot with Bobby Scherer in this, and I follow very closely, but she's done all the work, and it's really great. And she's going to tell us all about what they've done, and I expect to learn a lot myself. So, Ellen, over to you.
So thank you very much. Thank you very much. And I guess I'd say that's not the right thing. This is the thing, I guess. Hello? No, this is it. Oh, that's it.
Then you can
walk
around.
Okay, good. So yes, this really I think of as almost a culmination of a lot of the work I've done, which started primarily in toxicology, and then owing to the unexpected invitation of a colleague to join him in Brazil to study exposures to mercury associated with small-scale mining, where mercury is used to amalgamate and extract gold from riverbeds and water, I had my first exposure to working with people. And of course, once you do that, it's hard to go back to the little white mice, but that was a very great change in my life. But this topic I want to talk about really reflects my experience in both toxicology and epidemiology. I want to make the case to you that toxicology is really an essential science for public health and for medicine. But it has a kind of insecure basis. And it's a healthcare-related science that has really resisted the kinds of perspectives and, I think, reforms that it really needs that have come with the adoption of evidence-based approaches and the subsequent methodologies that are embodied certainly within the Cochrane collaboration. So I would say that I've become really converted to the view of trying to convert my fellow toxicologists of the real importance of our field to adopt or consider the advantages of adopting first the philosophy of evidence-based decision-making, and then thinking about how we incorporate the principles and practices into our field. So first I want to say what is the definition of toxicology. And it's really a set of disciplines, because it can be organ-based, it can be systems-based, it can be biochemical, physiological, et cetera, that determine the hazards and risks of exposures, or what I think you refer to as harms, which makes us starting from a kind of different position. Why is it so important? Well, I think toxicology has always been important, but it hasn't always fulfilled the expectations and, I think, social importance of the field, partly because of its continued aversion, if I may say so, I'm going to speak frankly about my field, to adopting a much more rigorous approach to collecting data, analyzing data, and testing one's assumptions. Toxicology is, as I said in the paper that I circulated to you, I call it the science of prevention, real prevention, because toxicology is the only way in which we obtain information about potential harms in the absence of exposing human populations. I think it was David Ozanoff who once said that a catastrophe is an event big enough for an epidemiologist to notice it. But certainly, epidemiology requires the accrual of information of people who have been harmed before associations can be tested. So in no way can we really call epidemiology a science of primary prevention. Ideally, it's a science of secondary prevention, but usually because of the disagreements and difficulties and challenges in resolving uncertainties, it really sometimes doesn't even meet that demand either. So the only science we really have, and that's why I think the obligation on toxicology to become better, frankly, as a science, is toxicology. And in fact, one of the most interesting publications that I just briefly want to touch upon, which reflects the importance, was a study published some 4 years ago by two persons at the Harvard School of Public Health, in which they undertook, it's in JAMA, and I can dig up the reference and send it to you, but basically they were wondering or posing the question, what is the most effective intervention to prevent a widespread disease in the population? The disease they picked was asthma in children, and we all know that this is a very important disease. It has high social costs, high prevalence, and it can be very serious. And they looked at sort of three different interventions. One was going into hospital, usually in an acute episode. The other was education of the parents so that they could understand ways to reduce the likelihood of going into hospital with an acute attack of asthma. And then they threw in a kind of monkey wrench one. Since I've talked to them, they told me it was really a monkey wrench. They looked at environmental regulation of air pollution. I mean, there's something really way out there, isn't it? So they calculated the costs saved and the lowering of the incidence of cases of asthma, and guess which one? It was regulation of air pollution by 100-fold. So that, to my mind, I wasn't sitting there saying, yay, air pollution, yay, EPA. That'd be hard to say today. But the point being that, it really increases the burden, I think, on toxicology to get its act together. But it isn't together. And as a result, we have these great expectations and great needs for toxicology, but there are an awful lot of barriers to resolving critical issues, the way in which it's practiced currently. And it takes an enormous amount of resources to conduct what EPA and other agencies refer to as a health risk assessment. This is where you have a notion of the harm or the hazard. You've estimated or measured the likely exposures and the size of the population impacted, and you calculate the number of events that's associated with that harm and those exposures, and that then becomes your assessment to support intervention. There are also now concerns over impacts on animal welfare by the kinds of studies we use, which utilize very large numbers of animals, and even without really a sense of how we adequately power our studies. So that's disturbing. And it has also speeded up adoption of some new methods, which are primarily cellular-based or, in fact, even structure activity modeling. So the field is in a lot of turmoil right now, but I don't think it's really going to resolve this turmoil without figuring out why do we need reforms for toxicology. And my opinion is so we can really support transparent and clear evidence and understand and reflect on and respond to biases and uncertainties. And I said, of course, this is why I think it's important, because it's before exposure, it prevents harms, and in most countries now, toxicology is part of many national health policy systems, be they environmental, occupational, or otherwise. But we also need to have evidence that meets those goals, and in certain senses, as you know, when you're doing a study or an analysis within Cochrane related to medical practice, you have to meet the needs of your users. And each user group has its own specific demands as to how they define relevant evidence and how they define an outcome that is related to the desire for an intervention. And in addition, when it comes to the use of non-human subjects, as I mentioned, I would be remiss if I didn't here at Johns Hopkins, where we have the Center for Alternatives to Animal Testing, not to also add another social goal, if you will, outside the field, which is not to overuse or overburden non-human subjects in our research. So I know this is really preaching to all of you, that we really need to increase the transparency and thereby the acceptance of decision-making. And I'm sure you know many decisions that are made, for example, in environmental health, are highly contested. Sometimes these are for a variety of reasons, but in fact it's very difficult to resolve many of the disagreements that arise over such things as really what is the very low dose effects of arsenic on human health. And that should improve decision-making and certainly the efficiency of decision-making. Toxicology does a very poor job of using statistical models of inference and other models. And in fact, there used to be a course taught at this school, statistics for toxicologists. I don't think that's taught anymore. But I have to say that the dominant test in the toxicology research is a t-test. And I think we do need different methods and more relevant research. There are some responses to this. It's not clear if they're really going to answer the questions we need to have. Well, starting in 2014, and this was really done by John Samet because he was asked by the National Academy of Sciences to chair a committee for the National Research Council about what is going on with toxicology and why is it so difficult to make decisions in environmental and occupational health. And I call this is when the axes fell on toxicology. I mean, some of us had been murmuring about these problems, but now you really got the word, which is you're just not working in any systematic way. And you don't produce information that meets any standards of rigor, and it's very inconsistent. And there were two volumes published, actually one on solvents and one on benzene, saying, why did it take 12 years to come up with a risk assessment for benzene? What is going on here? And it uses too many animals. And there are even now some claims that have been advanced, and this has come out of actually even the preclinical toxicology database for the approval of new drugs, that some of the methods that are used to determine whether a substance has harms have not been well validated. Some of you may have read some of the studies, particularly in the area of Neuroscience and Neurological and Neuropsychiatric Diseases, where analyses of the toxicologic literature, and this was produced as part of the approval process for a new drug, were highly inconsistent and fundamentally unclear as to their relevance to human adverse effects. So the situation is really under siege. And the public confusion, I like this because I think this has become a very famous statement known as the one-handed scientist. And it arose some 40 years ago when Senator Ed Muskie had convened a panel in the Senate to talk about the dangers of depleting the ozone layer. And he said, okay, tell me what the answer is. Is this going to be a danger? So the first scientist says, I've got these papers here that definitely tells us this is going to be a danger. And he was ready to conclude right there that he had the information he needed, but another scientist on the panel said, I have another set of papers over here that says these papers aren't good enough to know the answer. And this is reported by Ira Flato, who's the science correspondent for NPR. And he concludes, in exhaustion, the senator looked up and yelled, will somebody find me a one-handed scientist? So that's still there. So these problems have now been recognized, and a great deal of work is going on about the methods, about really the very beginning of the process of a toxicologic experiment, such as how do we define a material that we're testing? Do we have any kinds of rules there that assure us that we have actually got a complete set or a complete snapshot or a complete dossier of the relevant information, and how do we test for bias within those studies? Decision rules are completely non-explicit. In fact, the science of toxicology is permeated by this concept known as expert judgment or weight of evidence. And in fact, for a long time at the WHO, decisions, recommendations were based on identifying one study. And that study was the key study. And all you did was how you defined it was the key study has never been known to humans outside of a circle of who knows who. But you take that key study, and from the key study you extract the information that will allow you to make a recommendation. That, of course, is ridiculous. But that was actually in practice until about 4 years ago at WHO. And there still is really no clear commitment to conflict of interest as a potential source of bias within the toxicology community. And I think this is a science that actually began more or less as a handmaid to the producers of consumer products, chemicals, etc. And so the issue of conflict of interest is very important. Now, however, the picture's definitely changed. If I had given this talk 5 years ago, and I did at the Society of Toxicology, where I was practically thrown out of the room, as you can imagine, I can at least now say there are movements underway for reform. Some of the most complete and largest investments, I think, have been done by National Institutes of Health. This would be the National Institute of Environmental Health Sciences. And they set up a program called the Office of Health Assessment and Translation, or OHAT. And they have really invested a lot of time in trying to figure out, can we develop some systematic, small s, more explicit and transparent methods for finding relevant toxicologic studies and incorporating them in some way that we can generate evidence for action. There's another very interesting project that's taking place at the University of California in San Francisco known as the Navigation Guide Project. And they've taken some different steps. I'm going to talk about two products, one from NIH and one from UCSF, but also along the same way, to develop some consistent and coherent methods for moving towards evidence-based decision-making. Now, the person who directed the NIH office, the one up top, has now moved to the EPA, Dr. Chris Thayer, and she is heading up the Integrated Risk Information System at EPA. Now, how much funding it's going to get, how active it's going to be, is at present somewhat unclear. But at least the EPA is keeping its interest in that area. Now, why does EPA have something called the Integrated Risk Information System? really pretty simple. You know, EPA regulates a whole range of things under different statutes. They've got pesticide laws, they've got air pollution laws, they've got hazardous waste laws, and they've got water laws. And, you know, different offices would analyze, say, the hazards of lead. Now, lead is used in pesticides, lead occurs in drinking water, lead is in the air, lead is in soils. Well, they were coming up with different risk assessments, so that seemed to be pretty crazy and inefficient. And so this office was established about 15 or 20 years ago to kind of have an integrated product that would direct thinking and actions within any office or program of the EPA that involved the same substance. Now, we have another system that's been set up here at Hopkins within the Center for Alternatives to Animal Toxicology called the Evidence-Based Toxicology Consortium. And I was hoping some of them would be here, but they are also working in this area at the same time. And of course, within the Cochrane collaboration, there are a number of groups that have treated areas that are highly relevant to toxicology. Most specifically, how do we handle non-human subjects as the source of our information? What kinds of criteria do we use? How do we look at sources of bias? So I don't want to say that nothing was going on here, but it sometimes had different applications. And I guess there were one or two that would touch on the issue of harms, for example, for preclinical pharmaceutical testing. But this is, of course, the front and center of toxicology. We're interested in what's going to hurt you. We're not interested in helping you. We want to make it possible that you won't need help because you won't be exposed to these harms. And so we are I have been spending a lot of time trying to persuade the toxicology community that we really don't need to reinvent the wheel, that we have the Cochrane-based effort, which, as you now know, involves over 50 years of thinking, validation, reforming, revising, and expanding the principles of evidence-based medicine. And you know what those are, so I won't really go through this. This slide is usually what I have to show to my toxicology friends. And it really deals, I think I highlighted something which, of course, within Cochrane falls under the domain of philosophy. The Cochrane philosophy really has a strong commitment to transparency and inclusion. Now, this is the first point where toxicology fails. This is where the first F comes, because we have this expert judgment and weight of evidence. How transparent can that be? When I showed this slide at the SOT, they practically threw a book at me. So there's the Wizard of Oz over there on the left. And, just trust me, I'm the Wizard of Oz, because do you know what the weight of evidence means? Are we weighing it? Is there any substance to this? Do we assign some kind of value where I say my evidence is heavier than your evidence? No, of course not. So, but this, and I like this statement by Doug Weed, where he said, it's neither a scientifically well-defined term nor an agreed-upon formalized concept characterized by defined fools. So it's really what I call the fog of evidence. And there's the poor Statue of Liberty caught in fog. But this is still, unfortunately, very rampant in the field of toxicology. And when I give a talk about this to any gathering of toxicologists, one of the reactions I got was from a senior colleague that I know quite well who said, but I am an expert. And I said, well, you got to prove it to me. Anyway, so if you had a little badge, like the Doctor of Thinkology in The Wizard of Oz, then I guess you can make pronouncements about a weight of evidence. And the other point is that while I certainly believe that we have much to learn and a great deal to emulate within the experience that you're all involved in here on evidence-based medicine and related fields, there are some differences. And Bobby and Kay and I have been talking about these extensively because we are mostly dealing with non-human subjects. There is human toxicology, of course, and there's forensic toxicology, etc. But when it comes to trying to determine whether some substance, such as mercury, is harmful to humans and at what exposures, we are actually not ethically allowed to test people with mercury. Now, I've had some colleagues who've come up with some interesting designs by which they might try to do that, like just let people eat a lot of tuna fish. But I can tell you that the IRB here considers if you're doing that for the purpose of finding out the harms of mercury, they won't approve it. Now, if people want to go out and eat tuna, you could do an observational study, notice I said people, and then determine whether people, say, living in the Faroes, where they eat a lot of fish and whales that have mercury, and compare those to people that don't, then you have observational data, but you can't really do experimental toxicology, certainly on people. That was actually outlawed by the Nuremberg trial. The other point, so we have this problem that we're not really using the same subjects. And even more so, as I'm going to talk about with the two examples, we are often, when we're studying a particular thing, such as arsenic and diabetes, well, our animals don't really get diabetes, if you know what I mean. They might have changes in glucose. They might have changes in insulin signaling. They might even have glycosylated hemoglobin. But do they really have diabetes, the disease? Not really. So we're always dealing with analogs, and not solely a different species. So very often, and of course when we come to neurologic diseases, the game is really off. I've seen a lot of crazy mice in my life, but I'm not sure if I could diagnose them as schizophrenic. Experimental studies are often conducted at much higher concentrations or doses than found in human studies. Now that has been argued for a long time in the field by saying that because they have a shorter lifespan, we're sort of speeding up the process. And then we also are kind of like trying to be better safe than sorry. So if there's an effect that occurs at a high dose, then we have concerns for lower dose. There's a lot of, intellectual jujitsu behind those assumptions, and they are continuously challenged. It's very clear that the data are contradictory, and there's some very obvious reasons for this, as I'm going to show you in the examples. So it makes it very difficult to do meta-analysis. The other point, now here we come to what do our stakeholders want, which is a little different, I think, than what you have in terms of the demands from the clinical community, public health community. Most environmental and occupational and other related agencies around the world have determined that it's important to know the mechanism by which an exposure causes a harm. I don't think you're actually required to do that in terms of evaluating whether an intervention causes a benefit or whether an epidemiologic study shows that arsenic is associated with diabetes in humans. I know people will make some hand-waving about mechanism. I have to admit, I'm going to slang you guys in epidemiology. Mostly people say, well, it's really due to reactive oxygen or oxidative stress. Well, you could say that about everything, including why rocks weather under the ocean. So that's not actually very informative. But the problem is when you say we want information on mechanisms, we really have very little knowledge or consensus on mechanism for, say, even how lead affects the development of the brain. We have 5 or 6 theories and models, all of which have some compelling observational, that is, experimental evidence, but I can't say I know how lead reroutes the wiring or organization of the developing brain. So it's unclear what we're going to do about this topic, but it is unfortunately one of the things that our stakeholders really want. And of course, we get relatively little mechanistic data from human studies. We observe things, we measure biomarkers, but do we understand the mechanisms, the mechanistic pathway of many health outcomes? Probably not. We use biomarkers, but they're not necessarily mechanistic. They're signals of something going on, but do they fit into a mechanistic structure of explanation? Unclear. So I have concluded a long time ago that we really, while we have models from Cochrane, and we certainly have models for practice and philosophy, we do need something that answers the specific needs of our discipline, the limitations of our science, and the desires of the public and our stakeholders. There are, right away, as I said, there are fundamental differences in purpose and practice. The purpose in toxicology is to identify harmful exposures. Some studies examine efficacy of interventions to prevent harms, but this is relatively rare in experimental toxicology. Our subjects, I say here often, but in almost all cases are non-human animals. There are some countries where certain amounts of testing are allowed, and particularly with respect to pesticides, and there was a great political uproar about 6-7 years ago where several pesticide companies wanted to utilize these data, and one country that allows this is the United Kingdom, but the EPA decided no, they could not use these data. And I actually ran a test. I took one of their studies and I submitted it as a study that I wanted to do to our IRB. And I got a call from the IRB and they said, "We're hoping this is a joke." And I said, "Well, it's kind of an experiment." And they said, "That's good, because if you really meant to do this, expose children to a pesticide to find out what an adverse effect was, we would have to report you." So, and the methods are so diverse within toxicology, as I mentioned. Traditionally, toxicology used whole animals and tested them through various routes of exposure. Increasingly, we use in vitro studies, which could be excised organs or cells, and then, as I mentioned earlier, this whole interest in computational toxicology, which is referred to as in silico modeling, primarily related to structural comparisons. You know, if this polycyclic aromatic hydrocarbon is associated with damage to the lung, then this one, which is very similar, may well be. And these translate, though, into practical differences, which several of us in this room struggle with all the time, and that has to really do with how we find the studies we want. We're using PubMed. There's something called, there's a toxicology database as part of the National Library of Medicine, but it really uses the same terminology and ontology, which doesn't always suit our purposes. It may be the same word, but it has different meanings. For example, I see Laurie back there, she knows this, the word exposure. I mean, this is fundamental to toxicology. And even worse, the word mechanism also has you can enter it into PubMed and you will get interesting things. You will not get what we want. And things like developmental stage could also be different. Anyway, we have some linguistic differences here, and we are working and trying to find out how to work on incorporating expansions of those sorts of, or reducing those sorts of barriers. And now I want to turn to some of my experience with using systematic approaches in toxicology. And I've found, and those who have worked with me on this know this too, that the search terms that we access through PubMed are not readily applicable. We run up against some walls. That's not the first time this has happened in the field of systematic reviews, so we can learn from your experience, but it is something we need to deal with. Of course, the major problem, which I've already alluded to, is toxicology studies rarely define outcomes in terms of human disease. Now, there may be a hand waving in papers. I've waved my hands and said, this study in which I've shown that there are changes in the wiring of synapses in the brain from low-dose exposure during the first trimester of development related to methylmercury, and this may relate to. But I never observed what it is that it relates to in the animal. I'm making an inference, a kind of play, if you will, for the significance of toxicology. But I didn't measure the outcome in the animal. I measured some biochemical and anatomical events that are associated with this exposure. I haven't measured these events in human brains, but I'm inferring that they have a relevance to an outcome of clinical or population importance. But there's a big jump there. The comparability of lifespans and stages are very difficult to define, and this is really important because we have great interests in the early prenatal exposures, early life exposures, exposures that occurred during aging, but we're dealing with animals that have very different lifespans. And are they exactly the same? For example, some animals do not go into a real menopause, physiologically defined. Others do, but they go in much earlier. So are we really looking at a model of the human menopausal transition and the way in which exposures might interact with that? Quantitation methods vary. You have very good models drawn from epidemiology and elsewhere by which you can actually come to a quantitative assessment of the size of an effect. We don't generally do that. We don't have baselines. We usually compare, quote, control animals to exposed animals. It's very different. Now, the other one, which is a little more philosophical, but I wanted to throw it out to you because it came up during a discussion I just led at NIH on what needs to be done to study lead. Experimental toxicology doesn't incorporate covariates. We have nicely raised animals with good mothers in clean cages with full nutritional support, light and day, and some people even add these kinds of environmental simulation of having some toys in the cage and things like that. So if we're looking at the effects of, say, lead in populations, where we have a situation that lead is so highly correlated with socioeconomic issues and stresses, which is a social and political problem, but we can't consider how this might play out in terms of the data might get from a toxicology study. One of the examples I'm going to give you is an attempt to do that. It's extremely difficult. So here are the two real-world experiences. One is from some time ago, and this represents the NIH approach, the OHAT approach that I mentioned earlier. And this was looking at the associations between arsenic and diabetes. And the goal was to find and evaluate evidence from both epidemiology and toxicology. I'm going to stress the toxicology, because you all know about the epidemiology side of this. So this is now looking at what they did. This is a Prisma representation of what happened here. And they found not that many studies, and they wound up with relatively fewer. They ended up with 76 studies as they went through this. They had 36 of them that had human data after they excluded, based on general principles of previously published, et cetera, or lack of obviously important data such as dose. And there were 21 studies with animal data. And they were more or less, they used those same animal studies to see if there was some data on mechanism. And so this is what they got. Finally, 20 studies. And I'm really, again, focusing on the toxicology evidence. The toxicology and the mechanistic studies were incredibly diverse. I mean, diverse beyond your worst fears. Animal species, duration and dose of exposure, route of exposure, and even the endpoint that was measured. So the outcomes included, as I mentioned, blood and urinary glucose, insulin, glycosylated hemoglobin, insulin resistance, other biomarkers, insulin-dependent global uptake, and my favorite, oxidative stress. So how do you put all of this together? How do you derive anything from this evidence? And the conclusion was the heterogeneity was really too great to do anything other than a kind of, narrative summary of what was found. But let me be really tough here. I don't think the toxicology added one whit of weight to the weight of evidence thinking about arsenic and diabetes. It was impossible to do it. So that wasn't very encouraging. So let's go to the other one, which I just looked at. This just came out. This is from the UCSF program, University of California, San Francisco program, which was developed by Tracy Woodruff, and it's known as the Navigation Guide, and it's an independent attempt to develop the same thing, consistent, clear, and applicable methods for finding appropriate studies, evaluating them, and then analyzing them in terms of reaching conclusions that are relevant to and capable of being used in policy making. So this, as I said, is the most recent. It's also interesting because of what it's doing. It's a fairly complicated study. Maybe they should have started with something not quite so complicated, but it's the most recent one I wanted. The question they were asking here, PICO question was, does exposure to both prenatal stress and exogenous chemicals result in a worsening of developmental outcomes compared to either exposure alone? And is there an interaction between prenatal exposure to exogenous chemicals and stress on developmental outcomes? Now, this is actually a pretty complicated PICO statement when you think about it. I mean, you've got a whole range of possibilities. Developmental outcomes is an enormous range of exogenous chemicals, and prenatal stress in itself is kind of a challenge to define either for humans or for experimental animal populations. But take it for what it is, because it's a very interesting example of practice. These were their definitions. Stress was considered chronic psychosocial stress. That comes, I think, from the human literature, or what they called equivalent in animals. And for the animals, they could define how they induce stress because they had to do it. So they would change the nest material, they'd restrain them in terms of space, they would have no light or bright light or heat. It's a little different from psychosocial stress when we think of it in the epidemiologic or human context, but there you have it. The chemical exposures that they looked at, and they did this in terms of was there a sufficient number of papers that would allow them to be analyzed. They weren't being selective here. Lead, alcohol, caffeine, methylmercury, arsenate, diesel exhaust, toluene, uranium, perfluorinated octanol sulfate, or aluminum. And as I said, these were not meant to mean the most important or the most prevalent, but they had data from both human studies and from animal studies in order to do it. Well, now we come to the outcomes. We have fetal growth, birth weight, birth length, head or abdominal circumference. That can all be measured in animals and humans. Preterm birth, gestational age at birth, and other outcomes within 0 to 12 years in animals and 0 to 12 years in humans and 0 to maturity in animals. Possibly an important difference, because you're here definitely using the same endpoint, which has to do with sexual maturation, but it's not exactly the same. But they were trying to make things as consistent as possible where they could. This is their PRISMA statement, and this is really, gives you an idea of the state of the toxicologic literature, may I tell you. So they did their assessment, and they came up with an enormous number of papers. And even after they got through, they searched twice. And when they removed the obvious duplicates, they still had over 16,000 papers. They screened them, and that threw out almost 12,000 of them. And then when they did a full text assessment, they lost an additional number, so they were down to 265. And eventually they had 69 studies that could be used for qualitative synthesis. There was probably the limitations from the experimental data, more than the epidemiologic data. And the studies that could be used for quantitative synthesis or meta-analysis was 4. Now, I want to stress that most of the loss came from the toxicology side, not from the epidemiology side, which says a lot about what's going on in my original field. The heterogeneity, again, would make your head explode. The animals, different species, rats, mice, monkeys, we're not even in the same genus here, and dosing was, they just decided to divide it as high or low. Now, from my reading of the study, I don't know if they actually had a stable divider, or did it vary in terms of each study, that it was characterized as high or low? And in the animal studies, there were very small sample sizes. I just want you to know the field of toxicology is not concerned about statistical powers. So that's why when you look at it from that point of view, you usually don't see any evidence that there were a sufficient number of animals used. I will remember, before I was enlightened and converted by coming into epidemiology with Kay here, I was at NIH and I had done a study and I was trying to do some statistics. It was a longitudinal study over the lifespan of mice, and it did occur to me that maybe a t-test at each point in time was not the right statistical model. I don't know why I was so prescient, but I went to see the Laboratory of Biostatistics at NIH. This poor person who's probably sick and tired of experimental scientists coming over, he said, "What was on your mind when you designed this study?" And I explained. And he said, "Why did you think that having 8 animals was enough?" And I said, "Well, 8 animals is a big study in toxicology." I don't think it's gotten much better. I'm really sorry to tell you this. So this is a picture which just looks at the humans are in the dark bar, and they show how many of the studies actually included certain outcomes. You can see there are a lot of outcomes here. And when they were looking, you look at the sort of stable outcomes, as you might say, which would have to do with things like fetal organ weight, day of development landmark, birth weight, fetal size, etc. But then there are all these other ones that are very complex endpoints to measure, like behavioral outcome. I mean, that could be a lot of things. Or like skilled motor activity. I'm not really sure how that was measured in the rats or the mice, or whether it was different. So you end up with something that, what do you do with this kind of information? Remember, you're dealing with 4 studies that you're going to do quantitative work on. So conclusions. Are we really able to compare or integrate epidemiologic studies to non-human toxicology? I would say at this point we are not. And I would say the major flaws come from the weaknesses in the toxicologic data. But then there are some inherent practices, such as the wide variety of species that are used and the wide range of outcomes that we would call, say, developmental outcomes, instead of picking one thing or a symptom cluster, such as what Skackelbach has called testicular development disorder associated with exposures to endocrine disruptors. Can we improve toxicology? I think we can. But of course, toxicology thinks it's wonderful in its current state of activity. I think we have to really do something deeper, which is to say, we value you, we want to be able to use your data. And when it comes to setting preventive measures such as regulations, we have no other source of data. So we have to improve toxicology. And we have to deal with some of the more difficult problems, which are things like differences in lifespan, metabolism, and outcomes. And as I stated, and I want to state again, rodents don't get dementia. Rodents don't get diabetes. They don't get an analog of diabetes. In fact, it's very hard to get an animal to have a stroke. You can do horrible things to the animal, it will have a stroke. But if you just increase, and it's hard to raise blood pressure in rodents. One reason, because they walk on 4 legs. Just think about that physiologically, okay? So many of the things that are related to increased blood pressure in an erect, Homo erectus, are different from something that's crawling around on the ground. So maybe there are some diseases that are going to be extremely difficult for us to model. We hope that we can see analogous mechanisms, but we don't really have a good grip on mechanisms. Probably somewhat better in animals, but of course we don't have the outcome, so who knows whether our grip on the mechanism is important. But we can't use that to build a bridge across toxicology and epidemiology. So I think what we've been trying to do, with great help of people in this room, is try to bring together an international community of practitioners in both epidemiology and toxicology to move forward. And some of these are just the methods, such as the ontology, identifying new terms and appropriate search terms, and some are much deeper. And we do still have to demonstrate the value of the systematic review approach to policymakers, stakeholders, and toxicologists. And I have to give a real shout out now to Chris Thayer, whom we've moved from NIH to EPA and is in charge of the office where this would happen if it continues to happen. And she seems to have somehow cast a magic spell over the new administrator of the EPA, where he thinks, oh yeah, this is going to get rid of all these annoying environmentalists because we're going to have real evidence here. So I hope this holds out. But I think, it's one of these programs coming in at a time where it's under a lot of challenges. Of that, there really is no question. And so that's my talk.
Great. I mean, it's my first exposure to the whole field. My question is related to, changing a field is very extremely difficult. It may take more than one generation to do it. So
Well, that's what Kay is always telling me. She reads me the history of the reaction of the clinical professions to the idea that maybe we need evidence rather than art and judgment. So we have the same words, the clinician saying, but I know this works. I have clinical judgment. And the toxicologist saying, but I know this is not harmful. I have weight of evidence. So, yes.
So my question is, for the current generation who are going through their graduate training, for example, here, what are the type of curriculum that you sort of have injected the idea of evidence-based toxicology to the education of the newer generation?
I haven't had very good luck with that. And sometimes when I'm feeling, really masochistic, I go to the Society of Toxicology meetings and give a talk on this subject. And I say, I think toxicology is the most important science in the world, but not the way we're doing it. Not well received. And then the problem is, the 2 examples I gave you Let me put on in my hat as a regulator at EPA, and some of us have encountered this. You were there, Bobby, at one of those meetings. If we present those examples, they say, well, it doesn't look like you're ready for prime time, so it's a problem. Maybe what would you suggest from the history of Cochrane? How do you persuade a group that has formed its own cult and believes its practices are perfect?
We haven't been successful yet, but I'm sitting here thinking of the fact that we've brought all these people who they buy into the ideas and then they decide that their methods are okay. And in a way that's good, because it can't just be a tiny group of people who change a field. It has to be embraced by a much bigger group who then use methods. But we have a lot of bad methods now because because of the good where people have embraced. So that, I think, is also a challenge.
Well, in effect, we're sort of there, because almost every regulatory agency in the United States, really following on the blast that John Samet published, has said, oh yes, we believe in systematic methods. And the WHO says, we believe in systematic methods. And even that part that used to have the key study says, we believe in systematic methods. So everybody is, saying the words. And I think now maybe the burden is shifted back for us to say, well, actually, we can deliver. But I have to say, when I read this paper that just came out from UCSF, from a very smart group that's put a lot of effort into it, and I don't think it was their fault. I think it's when they started to look at the literature, it just didn't meet the a priori criteria that they've spent a lot of time developing for inclusion. So we've...
True of medicine, too.
True. Yeah.
Fantastic. I was curious as to why you stopped at primary prevention and why you didn't think toxicology could, or if I understood correctly, why you didn't think toxicology could help with secondary.
Oh, I think it can. I just wanted to claim primary prevention for my science. Because you don't do primary prevention. That's why. I'm sorry. Yes, of course it can. Yeah. Yeah.
Another aspect that I wanted to chat about was the sample size issue and how that relates to ethics and how
Yes.
various groups have put up very reasonable opposition to just backwards in research and how we should be restricting and all that. So
Right.
I wanted to know your thoughts.
Well, you're right. There is a very strong push, very strong in many European countries, but growing in strength in the US as well, about the overuse of animals in toxicology. And one of the points I've been discussing, particularly with the group here at Hopkins, because I think it really needs to be made, one appropriately powered study can replace 10 wretched studies. So you shouldn't just look at the number of animals in a study. What you should demand is much better design of studies. So I think you're absolutely correct that has been used, and I can certainly tell you the chemical industry is a great supporter of the animal groups that don't want animals used in testing. I wonder why.
Ian stole my first question, so I'll ask another one. You talked about the heterogeneity of all the different studies, which is not particularly unique to toxicology. I mean, that's what we've seen in some of our systematic reviews of medicine. There's quite a variety of ways that people look at some of the different species.
That's a big difference. I mean, even if we weren't interested in human facts, if I'm supposed to be taking information from rodents and primates, leaving the humans out of the picture for the point, that's an obstacle.
Anyway, so I guess my question is, what's the way forward with that? Is it to try to enforce some standardization of the studies, or are there methods that can be used to merge these different outcomes?
Well, of course, the FDA really does impose a standardization. They have specific animal models to be used to develop preclinical toxicology data. But since an awful lot of the information that goes into regulatory processes at, say, EPA or OSHA comes from places like this where nobody tells us what to do, right? And if I want to use fruit flies, I'm going to use fruit flies. So there's not really, hasn't been a fiat to go down. And remember, we have the great specter of thalidomide in our field. I don't know how many of you know the thalidomide story. Well, thalidomide was tested primarily in rodents, maybe in dogs as well, in Europe, and then approved for use. Now, it was coming to the United States, and Dr. Frances Kelsey, who was a toxicologist at the FDA, just thought it really needed to be tested. So she threw in some rabbits, and that's where the effects turned up. So we have this little nightmare that we really don't know what is the appropriate animal model. And it might differ in terms of the outcome we want to look at. I mean, I have yet to see a good animal model for diabetes. There's some diabetes-prone mini pigs, and that may be useful, although it's a genetic disposition, but you could look at, say, aggravation. They get what resembles a clinical form of human diabetes. So maybe we have to think more carefully about what it is we're looking for. But this is something, when you say, I think you should only use rodents, then you think, oh no, thalidomide. Yeah.
Are there any efforts for registration of toxicology studies in the clinical trials world on publication bias is a major issue, and I would suspect that it's a larger issue in toxicology?
Well, since we don't think that conflict of interest is a problem, I suspect we have a lot of that. In fact, there was a very nice analysis that was done on the topic of endocrine disruptors, which is a group of chemicals that affect the development and function of endocrine hormone systems, whether these are thyroid, whether these are developmental, or whether they're neurological, whatever they are. And they did an analysis showing what were the outcomes reported and conclusions based on the source of funding. And I know you'll be just horrified to find out that all the studies funded by the chemical industry found very little effects, while the studies that were done by academia found effects. So we probably have an awful lot of bias. But it's not required. I mean, if you go to toxicology journals, it's not necessarily required. I tried to introduce, I was feeling like bored, so I was at a toxicology meeting and I said, I think we should have in our bylaws for people who are admitted to the society a statement about conflict of interest. Oh no, we value our industrial colleagues. So maybe it's better to have them in the tent not, but there's no real consideration. And of course, if you're using these interesting terms like expert judgment, how much of that is biased? Probably a lot. Expert judgment tends to be biased by your own experience because I'm an expert and I've always found this to be true. So I think it's embedded and really hard to quantitate.
Do you ever deal with the other side of the spectrum, the sort of conspiracy theorists, say vaccines or GMO or those kinds of things which people get all worried about? Maybe
Very much. In fact, I'm sure somewhere there's a little place in hell that has been reserved for me after I wrote my book about industrial agriculture, where I had the temerity to suggest that we need to produce more food globally. And I also said, I didn't write this book for the 1%. The 1% I have always observed takes care of itself. And so they can read Michael Pollan and spend $100 to buy a chicken. I'm writing for the rest of the world. Yeah, you're right.
I'm sitting here tweeting, so I'm a little behind. Trying to tweet what you say.
Uh-oh.
Uh-oh.
No, she's engaged in a tweet-a-thon with our dear leader, right?
Well, I think this is very important that we get the message
Yeah.
out. I know some of you students have taken the toxicology course, and I think that we're in public health. And
Is there anybody from toxicology in this room?
But everything
We have
you
to
say
hold
is-
them captive.
I know, but when you talked about changing a field, that's when maybe we can work
You
on
have
some
some
of this.
experience. I know.
trying,
I call you up every once in a while.
We're
Say,
trying.
is it ever going to change?
So thank you all for coming, and thank you very much for
Thank
your
you.
provocative presentation. Thank you.
Thank you.